Okay, so we have been going through the basic trigonometric functions and their properties. So far we have seen quite a few things, and we in fact also saw in the last video their graphs and their periodicity. So here we are going to see which one of them are even functions, which ones are odd functions, and also we are going to look at some basic trigonometric identities. So let's first see the evenness and oddness. Even versus odd. From the graphs of the trigonometric functions we see that the cosine and secant function are even, and the other four are odd. Which simply means this. Let me do it over there. I won't have space here. So on the left side we have the even functions, and on the right we have the odd functions. Cosine is even means cos minus x is equal to cos x. Secant is also even. And the other four are odd. Sine minus x is minus sine x. I can, to distinguish things, put one vertical bar here also. And its reciprocal is also odd. Cosecant function. Then tangent is also odd. And finally, cotangent is also odd. Now, besides getting these facts from the graphs of these functions, you can also directly look at their definitions. From there also you can see that, for example, the cosine function is an even function. How you have to look at that fact is just this. To apply the definition, the actual definition of cos x to the present situation, and that is to actually go back to the meaning of cos minus x, say x is a positive real number. You have to, of course, again draw that unit circle centered at the origin. So the thing here will be like this. So this is your x radian which is in the counterclockwise sense. The rotation is in the counterclockwise sense, so it is positive, and the corresponding minus x radian is this angle where the rotation is clockwise. So the terminal rays of these two angles, the first one is this, which intersects the unit circle here, and for this one the terminal ray is this, which intersects the unit circle here. Now because of the numerical equality of these two angle values, that is both of them are x, these points of intersection lie on the same vertical line, which you can see from the symmetry of this geometry. So that means, and because we have chosen the unit circle, so the coordinates of this point will be what? Cos x, sin x, by the definition of cos x and sin x. And again, the coordinates of this point like that will be by definition cos minus x, sin minus x. Now you can see one thing directly from the geometry, and immediately is that cos minus x and cos x are actually both the same thing, because it is this distance, and I say distance because it is actually positive in this case. I mean, the way we have taken these angles, both of these things are positive, and both of them equal the length of this line segment. And in fact, that is why you are having the x coordinate equal to cos x, and here the x coordinate equal to cos minus x, and they are equal. So that's why you have cos minus x equal to cos x. Sin x and sin minus x, on the other hand, they are not equal, but they are the negatives of each other. Why? That is because these two lengths are actually equal. However, this one is positive in value and this one is its negative. So that's how you get sin minus x equal to minus sin x. That is, if you add this length is equal to this length, but when we write it as a coordinate, we attach a minus sign with that positive real number, which equals this length. So if you add this with this, the signed lengths, that is not just lengths but lengths and with the proper sign attached to them, then you get that sum to be equal to 0. That's why they are negatives of each other. And the same thing you can also do with the other functions, and also for example for other angles which are not necessarily acute angles. You will see that these relations are always true, provided of course sometimes you have to take into account that fact that for some x, for example tan is not defined. Okay, so that has to be taken care of, but other than that these relations are always true. I mean, whenever they are meaningful, then they are true. For example, here you cannot take x equal to pi divided by 2 radian, because that is not defined. For other values of x where tangent is defined, this relation will be true. So this can be seen either from the graphs of these functions which we saw in the last video, or directly from the definition also. So that is evenness and oddness of our basic trigonometric functions. Now we go to the trigonometric identities. So to see the trigonometric identities, the very first identity is in fact the, okay, let me just write the heading also. Identities. The first one is, of course, the one we are most familiar with. So we again draw a diagram like this of a unit circle centered at the origin, roughly. So now here what we do, instead of taking an acute angle, we take an obtuse angle, for example. Say our angle, of course, in its standard position has this initial ray, that is the fixed ray, and the terminal ray is this one. So the angle is this, x radian. Then what we do, the point where this terminal ray intersects with the circle, from that point we drop a perpendicular on the x-axis. So that's how we get this right-angled triangle. And again, by the definition of our trigonometric functions, the coordinates of this point are cos x, sin x. So you can see one thing, that because the coordinates are this, you can of course also see that from the position of this triangle, cos x is actually negative here. The coordinate cos x is negative and sin x is positive because it lies on the positive side of the y-axis. But whatever the signs of these coordinates are, we can always have the lengths of these line segments, these sides of the right angle triangle, which are not the hypotenuse, by taking absolute values of these quantities. This is the absolute value of cos x, and this length is the absolute value of sin x. So if we now apply the Pythagoras theorem on this right angled triangle, so we can just simply somewhat, not very formally because I have not written anything for this diagram, but you can understand what we are doing. So we directly write, instead of writing all those formal things, applying the Pythagorean theorem to the above right triangle, we get what? The sum of the squares of the lengths of these two sides equals the square of the length of the hypotenuse. Now because we have considered this, we have taken a unit circle, so the length of the hypotenuse is actually the radius of this circle, so which is 1. So that means we get this. Now because we know that for any real number r, the square of the absolute value of r is just equal to the square of r. So now you can write, you can get rid of the absolute values and have the formula that you already know very well. Or sine squared x plus cos squared x equals 1. Okay, so that's how you get this formula from the Pythagorean theorem, and it does not actually matter what x is. No matter what x is, and consequently no matter where this terminal line ultimately falls, this relation is always true. That is, this relation is true for any real number x. You can convince yourself by taking different values of x and seeing whether you really get this thing or not. Now, from this we can get two others, which also you probably already know, which involve the other trigonometric functions. Dividing the above equation or dividing on both sides of the above equation by, say, sine square x, we get, so the first term will be 1 and the second term will be cos squared x divided by sine squared x. On the right side we will have this, or 1 plus, because this is cot square x and this one is cosecant square x, you get this, which relates cotangent and cosecant. Because we again are going to need it, so let me just number it. Dividing equation 1 by this time cos square x, we get the other relation relating secant function and tangent function. Sine square x divided by cos squared x, and this of course will be 1, and on the right side we have 1 divided by cos squared x, or tan squared x plus 1 equals secant squared x. Now, because we have obtained these other two relations by dividing the original equation by something, so that something by which we are dividing should of course be non-zero, because you cannot divide by 0. So in these other two formulas, here of course this is true for all real numbers x, but in these other two formulas you have to take care of the fact that the thing by which you are dividing should be non-zero. So here, for example, you have divided by sine square x, so you have to avoid those x values which make sine x equal to 0, that is all the multiples of pi radian, all the integer multiples of pi radian. So those x's are not allowed here in this formula. For the other real numbers, this formula is true, it works. Similarly, here you cannot consider those x's which make cos x equal to 0. That is called the odd multiples of pi divided by 2 radians. So other than those x's, for other real numbers, this formula is true. The first one, however, is true for all real numbers x. Now, besides these elementary formulas, you also already know from your previous trigonometric courses the angle sum formulas. And I need ink. There are two main angle sum formulas for two real numbers, any two real numbers a and b. Cos a plus b is cos a cos b minus sin a sin b. This is one. And the other one involves the sine function. Here also a and b are any two real numbers. Plus cos a sin b. The proofs of these two relations can be found in any trigonometric course or any trigonometric book which has these things, or you can also try to find it yourself by going through the definition and looking at, for example, special values of a and b. That will give you an idea of why the general one is true. It's a little more difficult than these first three because you are adding two angles a and b. So not only it's not enough to just simply consider a and b to be any two angles, because you also have to see what a plus b ultimately is. But anyway, for any two real numbers a and b, these two things are true. And using them and the evenness and oddness of these functions, we can get the other two formulas which look like this, but they don't have sum, but rather they have difference, which we can let us just do it. Although in the text that thing is there in the exercises, but let us do that here itself because it's very easy. These give rise to the following two formulas. The first one, let us find this cos a minus b. Cos a minus b can be thought of as cos a plus minus, can be thought of means actually a minus b means a plus minus b, a plus minus b. So we can apply our formula that we see here, cosine of the first angle times cosine of the second angle minus the product of their sines. So cos A cos minus B minus sin A sin minus B. Now we have already seen that the cosine function is an even function, so cos minus B will be cos B. But the sine function is an odd function, so sin minus B will be minus sin B. So that minus and this minus, they will give us plus. Plus sin A sin B. So that is the formula for the cosine of the difference of two angles or difference of two real numbers. And let us now next see the sine of a difference. Sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. Sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. Again, using evenness of cos and oddness of sine, we get this. Sin A cos B minus cos A sin B. And using, in fact, again these four, 1, 2, 3 and 4, you can find many other formulas which you, I think, have already come across in trigonometric courses. Now, among all those formulas that can further be found using these four and the first basic three, there are some particularly important ones. We have, for example, the double angle formulas. Using these two formulas or relations, one of them is of course cos square x plus sin square x equal to 1, and okay, this will come afterwards. First, double angle formula means here A will be equal to B. Taking A equal to B in the angle sum formulas, we get what? Let us see. Cos A plus B, but we can take B equal to A because that's what we have assumed here. So that means cos 2A equal to cos A cos B minus sin A sin B. But cos A because A is equal to B, so that means cos square A minus sin A sin A, that means sin square A. So this is a double angle formula where we have taken twice the angle cos 2A. Just like that, there is one for sine, which comes from the sine summation formula. sine a plus b, that means sine a plus a is sine 2a, that is equal to sine a cos b plus cos a sine b. In our special case, that becomes sine a cos a plus cos a sine a, that means 2 sine a cos a. So this is the sine 2a formula. Sine of 2a is 2 sine a cos a, and cos of 2a is cos square a minus sine square a. Now we can go to that thing that I was going to write here. Using cos 2x equal to cos square x minus sine square x and 1 equal to cos square x plus sine square x, we will get two things. First, if you add these two equations, you get cos 2x plus 1 minus sine square x and plus sine square x will cancel out, and here you will have 2 cos square x, or cos square x equal to 1/2 of 1 plus cos 2x. And if you subtract means if you subtract this thing from the second equation, then you get 1 minus cos 2x equal to sine square x plus cos square x plus sine square x minus cos square x. So now cos square x and minus cos square x cancel out, and you have 2 sine square x's. So that means 2 sine square x, or sine square x equal to 1/2 of 1 minus cos 2x. Here in place of x, if you write x divided by 2, you can write, because here in place of x actually you can put any real number. Since we have sine and cosine, there is no restriction on the argument x. So doing that, you will get another version of these formulas. Replacing x with x divided by 2, we get cos square x divided by 2 is equal to 1/2 of, there 2 and 1/2 they will cancel out, and we will have 1 plus cos x, and doing that to this one gives us sine square x divided by 2 equal to 1/2 of 1 minus cos x. And if you do this, replacing the argument by 1/2 of it here with this double sum formulas, then you get double angle formulas, you get half angle formulas. So those formulas you can of course see will be this: cos A is cos square A divided by 2 minus sine square A divided by 2, and sine A is 2 sine A divided by 2 times cos A divided by 2. Now besides these, you have another thing called the law of sines, law of cosines, or law of cosine rather. Which is a generalization of the Pythagorean theorem. It involves a triangle which is not necessarily a right angle triangle. And the way things are given in the text, we are of course going to see that. So it is, the diagram is this. Let me first draw the diagram and then we will see the law of cosines. So here what we do, we are again going to draw a coordinate system with x and y axis. And we consider a triangle like this. Actually, the law of cosines is applicable to any triangle, but we are considering one particular case. This is the problem of having a geometric definition of something and also geometric proofs of things related to that definition. There are so many cases, in fact infinitely many cases, that simply this type of proofs actually are not proofs, because you have to consider all different types of triangles. You can have geometric proof, but you have to carefully take into account all the possibilities. Simply because we are going to derive the law of cosines for this triangle does not automatically guarantee that it is true for other types of triangles, but it is. You have to see that. So this is a triangle we have considered, one of whose angles is an obtuse angle, and we are actually we can take any of these vertices as A, the other as B, but let's just see what the author has taken. So the one at the origin has been taken as C, this one has been taken as A, and this one has been taken as B. So in the standard way of naming the sides of a triangle based on the names of the vertices, this CA side is B, its length is B. AB side has length C and BC side has length A. So the coordinates of the point A will be B comma 0, because the way we have taken this triangle, this B actually is the length, and that's why this is also the x coordinate of this point. Y coordinate of course is 0 because the point is lying on the x axis. And then because of these things, the coordinates of B will be what? Oh, one more thing is that this angle of course has to be also taken, otherwise how can we have cosine? This angle is say theta radian. Then according to the definition of cos and sine functions, the x coordinate of B is a cos theta, and that is this a cos theta, this much, and the y coordinate is a sin theta. Now we want to calculate the length, or rather I should say relate the length C with the lengths A and B of these two sides and the angle theta. And in doing so, we are now just simply going to use the distance formula that we have already seen in coordinate geometry. And that is why in fact we are writing down the coordinates of these 2 points. Now means we can directly write from the above diagram we have C square, that is the square of this distance, is equal to, keep in mind we are not using Pythagorean theorem or anything like that, we are just simply using distance formula from coordinate geometry. This is equal to sum of the squares of the difference of x coordinates and difference of y coordinates, usual distance formula. So x coordinate of B is a cos theta and x coordinate of A is B. So a cos theta minus B whole square plus square of the difference of the y coordinates, a sin theta minus 0 whole square. So we can now simplify things, expand the squares and see what we get. So this becomes a squared cos squared theta plus b squared minus 2ab cos theta, a cos theta times b, which is 2ab cos theta, plus a squared sin squared theta, and that becomes equal to what? Oh, okay, I am writing it as a continuous line, right? So plus b squared, a squared sin squared theta. So this, if you take a squared common out, then you get 1 cos squared theta plus sin squared theta. So we ultimately get this. That is, we are getting this. C squared is equal to this thing, which gives us a relationship among the sides of side lengths of any triangle, in fact, and the angle between these two sides is also involved, where those sides are the ones whose lengths appear on one side, and the angle is opposite to that side whose length we are considering on the other side. Now so this is a special case, when theta is pi by 2 radians, that is when this is actually a right angle triangle, we have, because for such a triangle also this law of cosines is true, so in that case we have c squared equal to but cosine of pi by 2 is 0, so that is equal to a squared plus b squared. So you get Pythagorean theorem as a it looks like the Pythagorean theorem is a corollary of the law of cosines, because it comes out as a thing which is a consequence of the law of cosines. In this particular case, the law of cosines becomes the Pythagorean theorem. But actually, okay, so it may seem like we have proved the Pythagorean theorem in this somewhat strange way, without using any geometric considerations. I mean, we are considering geometry, but without going through all those things in Euclidean geometry, all those elementary things that we use when we go to prove the actual Pythagorean theorem, that is considering the right angle triangle, then considering squares with those sides. So that it seems we are not doing that, and we have somehow bypassed that thing. However, keep in mind that we have done actually what? We have used the distance formula from coordinate geometry in order to write this relation, and the verification of, or rather the proof that the distance between 2 points is given by that formula, that thing itself depends on the Pythagorean theorem. So you cannot treat it as a corollary to the law of cosines, because the Pythagorean theorem is there. It was proved independent of these things, first using just not not coordinate geometry, but simply plain Euclidean geometry, and then using that we have found the distance formula. So it's just an observation, that's all. It's not a proof of the Pythagorean theorem. So here this section, small section on trigonometric functions, ends. After this we have exercises, which of course we are going to do in the next calculus video. So with this I end this video. If you want to say something, you can write in the comment section below, positively or negatively, whatever you may feel, or you may mail me also at my address, which will be there in the description. The link will be there in the description. And tomorrow we are again going to solve algebra problem from Lee's abstract algebra, and on Sunday we of course have our analysis. So that will be all for tonight. So see you tomorrow with Lee's algebra exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.